In this video, I'm going to start discussing what is called the measurement problem in quantum mechanics. So the measurement problem has to do with this collapse postulate of quantum mechanics, which says that a particle is in a superposition of states. So we have our state here, psi, and it's equal to these constants here, c sub I, times the eigenstates here, this lowercase psi, where the psi, like I said, is an eigenstate of some operator. So this is just a generic operator that gives an eigenvalue, where the eigenvalue is the measurable quantity. The Born rule says that the probability of measuring some outcome is equal to the square of this probability amplitude here, or if we want to be more precise, it's multiplying by its complex conjugate. But it is also the case that if you immediately repeat the measurement, then you will get the same result as the first measurement. And so this is illustrated nicely, I think, with the Stern-Gerlach experiments, where if you remember from a previous video, we have some magnets here where this one is, say, north and this one is south, and we are shooting a particle through it that has spin, and when it goes through here, it will either choose to be spin up or spin down, whatever we mean by choose. And that's kind of the thing in question here. It's sort of collapsing into either spin up or spin down. But then if you send it through another of these Stern-Gerlach sort of apparatuses here, so we have north and south here again, it will still be spin up. In fact, if you're shooting a beam through here, some will be spin up and some will be spin down. 50% will be spin up and 50% will be spin down. But if you only do a second measurement like this on the spin up ones, then 100% of them will be spin up. And so we saw in a previous video that the wave function spreads out in time. So if you do this fast enough, then what you get is that the collapsed wave function has not spread out yet. And so you will get 100% here. And I've talked about this in previous videos before, where if you do a Stern-Gerlach experiment, so say in this other beam here, we now do one where we are sort of looking at this in, this direction here. So this is kind of going in and out of the screen. And so it could go either, the beam could either go in or out of the screen. And so we're saying that this is sort of pointing out of the screen, that's pointing into the screen. And in fact, if we do the measurement this way, then we once again get 50% and 50%. And so it has not collapsed the wave function in the direction in and out of the screen. And so that actually has to do with with sort of the Heisenberg uncertainty principle, that you can't know the spin in the z direction and the spin in the y direction at the same time. But that's kind of going afield of what we are discussing here, but I just wanted to point that out. But the main takeaway is that if you do this measurement in the z direction, and then you do another measurement on just the sort of spin up particles in the z direction, then you will get 100% in the spin up direction there. So that's kind of what that is talking about. That if you immediately repeat the measurement, then you'll get the same result as in the first measurement. So we can sort of put that formally here. So we have our wave function that is a linear combination, that's a superposition of those. But if you do a measurement at time t2, then it will be sort of equal to one of these linear combination, or one of the components of this linear combination here. So in other words, the wave function collapsed to the nth eigenstate of this psi sub n and so this is looking at sort of the energy operator, which would be different than the spin operator here, but the principle here is the same, that if you do a measurement very soon after doing the first measurement, you'll get the same result. So put differently, and so this is a quote from the book that I'm following here, The Foundations of Quantum Mechanics by Travis Norson. So he puts it like this: when a measurement occurs and has outcome A sub n, so that's our state there, the quantum state of the system being measured ceases to be whatever superposition it might have been previously and collapses to the eigenstate psi sub n, whose eigenvalue is the realized outcome A sub n. And so this is sort of our schematic of the generic measurement device here. So remember, our measurement device consists of a pointer that is sort of, reading off what the value we're interested in is. So, if we wanted to be specific, then up here, our measuring device, so our I guess probe would be these magnets, and our pointer would be sort of the screen that these will then come and hit there. But if we are just looking at a sort of generic or general measuring device, what we're interested in is that we have something that reads out the data, so the outcome, and a probe that interacts with our system. And then we have a system here. So say we have a particle in a box system. And so then the question is, what do we even mean by measurement? And so to make a measurement, we need an instrument that somehow interacts with the particle, and in so doing causes the quote-unquote collapse. And so we have our probe here that's causing the collapse. So in the Stern-Gerlach experiment, that would be the magnet sort of causing the collapse either to the spin up or to the spin down here. So that is what we mean by collapse. So the measuring device itself is a physical apparatus that is also composed of quantum systems and undergoes a physical change of its own in the act of measuring. So suppose we have our particle in a box. So we're sort of looking at this sort of setup up here. We have a particle in a box that can have one of three states. So we have this linear combination of these three states here. We have the measuring device with its probe inside the box and its pointer pointing at, say, just the y sub naught. So no reading, so no value there. And then we'll point to either y sub 1, y sub 2, or y sub 3, depending on which state the system collapses into. So the measurement interaction, so the particle with the probe occurs, and we get, say, the y sub 2 here. So the pointer moves, so using a force. So some force has to, push the pointer. So we have this F equals ma acts upon it, where m is the mass of the pointer. But what causes the force here to act on the pointer? So presumably it's some, classical mechanical force. There's some kind of gears or, whatever motor, something inside there that is sort of pushing on the pointer to move it. But then what causes the mechanical force? So presumably some classical electromagnetism, so following Maxwell's equations, occurring through the wires. But what starts the electromagnetic fluctuations? So that would be some change in the probe. But what caused the change in the probe? It was an interaction with a quantum system. So up until that point, the descriptions were all in classical terms, not quantum mechanical. So for example, we do not talk about the wave function of the pointer. So, we're saying that there's this classical particle in a box and this quantum particle in a box, and it's interacting with our classical probe here. So we're not discussing the probe in quantum terms. So our description, therefore, presupposes that quantum systems exist in addition to classical systems. So we end up with this kind of dualism here, where some particles are quantum mechanical, so wavy and probabilistic, and others are classical, so definite. They have definite values of position and momentum and those kinds of things. They're unambiguous. and unsuperposed, so they don't have a superposition. But then these two realms have some kind of rules dictating their interaction during a measurement, which causes a quote unquote collapse of the wave function. And so, what kind of physical processes even count as measurements? So this is a quote from John Stuart Bell, who of the Bell's theorem fame, and we'll talk about that at length in future videos. But here he is talking about the measurement problem. So he says, what exactly qualifies some physical system to play the role of measurer? Was the wave function of the world just waiting to jump for thousands of years? So it's sitting in its superposed state for thousands or millions of years until a single-celled living creature appeared. So something that could observe or measure it, or did it have to wait a little longer for some better qualified system with a PhD? If the theory is to apply to anything but highly idealized laboratory operations, we are not obliged to admit that more or less measurement-like processes are going on more or less all the time, more or less everywhere. Do we not have quantum jumping, which by that he sort of means a collapse then all the time? And so, presumably quantum systems, which make up everything, are interacting constantly with classical systems, which also make up everything. And so which of those interactions counts as a measurement and which ones do not? So in other words, if a measurements occur by interaction of classical systems with quantum systems, then why are some of these interactions called measurements and others not? So let us try treating this particle detector completely quantum mechanically. So we're looking at our probe and pointer system again. And so we want to treat it quantum mechanically instead of classically. So for simplicity, we'll just assume the particle pointer system. So the system, so we're only going to be looking at the pointer and the particle. But the same will work even if you decide to include every process along the way. But doing it this way will make it easier to work with. And so we have our particle with its three possible states here, and a pointer with the wave function is a Gaussian centered around the initial state. So our pointer has a wave function that's centered around this sort of no value state right at the beginning. So we'll call that phi here, and that's given by this right here. This is our Gaussian wave function centered around that y sub naught, where n is just a normalization factor that we're not going to worry about it too much here. So when the measurement interaction begins at t equals 0, the particle pointer system wave function is this. So we see that it's just a multiplication of those two systems right there. So the psi is our particle and the phi here is our pointer. And this will evolve according to the time-dependent Schrodinger equation that looks like this for our full system here, which is this uppercase psi, where this h hat here consists of three contributions: the particle, the pointer, and their interaction. So the particle Hamiltonian for the particle of mass m looks like this, and the pointer Hamiltonian for a pointer of mass capital M will look like this. But since this big M here is a lot greater than the small m by many, many orders of magnitude, we can approximate it as essentially being infinity compared to the small m. And so this will actually go to 0. So in the interaction, we want it to be the case that if the particle is in state psi sub n, then the pointer is pointing to the place that corresponds to the energy E sub n. And so an interaction Hamiltonian that achieves this will be this right here. So this is our interaction Hamiltonian using the canonical momentum operator here. So our p sub y is just equal to this negative h bar times the partial with respect to y. And so the lambda here is a constant that has to do with the interaction strength. This h sub x is the energy operator for the particle in the box. And so this is essentially saying that, whatever energy the particle in the box has, it will interact with the pointer with this lambda here and then cause a sort of momentum change in the pointer here. So we have the energy of the particle. It's going to cause a momentum change, and that momentum change will be scaled by this lambda times the particle energy. So if the particle begins in a particular state psi sub n, then the particle pointer wave function, as we said, was this, but we're now saying that this particle is in state psi sub n. So we then have the Schrodinger equation, and so what we will end up with is this right here. So our change in psi with time is equal to this negative lambda, this h hat sub x here, and then our partial with respect to y. And so the t and y dependence of psi are coupled, but x is not involved, which means that this is proportional to this psi sub n here of x, because the x will be just constant because it's not dependent on x, which tells us that the system remains in the eigenstate of h hat sub x, and so we can do this right here. So we can this h sub x here, it will remain in that state, so we can just give it the E sub n here, which is the eigenvalue for this h sub x, and it will remain in that eigenvalue because it's not changing with respect to x, which will then yield this solution right here. So this is our particle wave function, and this is our pointer wave function. And so this is telling us that it's moving to, it's pointing at something that represents the energy E sub n here. And so if the interaction goes until time t equals capital T, then we have this right here. So this is just, it stops pointing at, or it stops moving at t equals capital T, which means that the particle remains in the nth eigenstate while the pointer moves a distance that's represented by this and is now centered at y sub naught plus this, which we can call y sub n, which is the nth energy value because we're looking at E sub n right here. But now what happens if the particle is not in a definite energy states? So far we've been looking at if this is in a definite energy state, but what we're interested in is if it's not in a definite energy state. And so then we have the wave function at time t equals 0, which is a linear combination of all these possible states right here. And at time t equals capital T, we get this. And so this energy here is also a linear combination of those energies. And so it's not pointing at a definite place. The pointer is not pointing at a definite energy value readout, which means that the particle and the pointer are in a superposition of states. So the pointer is pointing at y sub 1, y sub 2, and y sub 3 sort of all at once. It's sort of smeared out in all three of them. And so if you are already familiar with these sort of Schrodinger's cat sort of thought experiment, you can see how this sort of leads to that Schrodinger's cat experiment where the sort of readout, which in Schrodinger's cat is the cat being alive or dead, is sort of smeared out between all these different states here. And so and I'll talk about the Schrodinger's cat experiment and actually get into, what that experiment actually was and stuff like that in the next video. But for now, the thing to point out is just that we're saying that this classical system, or what we usually think of as a classical system, this pointer, which is, that big pointing thing on our measurement device, is, if we look at it quantum mechanically, then we would have to say that it would be completely smeared out across these multiple different values here. But, I think you can be pretty sure that you've never seen anything like that. You've never seen any kind of measurement smeared out sort of probabilistically between a bunch of different values. And we're not talking about, our pointer sort of vibrating back and forth really fast. We're saying that like it's literally, sort of, uh, you know, kind of a cloud here. It's sort of a probabilistic, you could maybe even transparent cloud between, the three values of y sub 1, y sub 2, and y sub 3. But like I said, you have never seen that. Nobody has ever seen that because that's not how things in classical physics works. But then we are stuck with this idea that we sort of have two realms of things. That we have the classical realm and the quantum realm, and that seems very unsatisfying because at what point, at what sort of scale can you say, if we zoom in just a tiny bit more, now we're in the quantum realm. If we zoom out just a tiny bit more, now we're in the classical realm. So, where is sort of the cutoff for that? And there are, you know, there are other problems with the measurement problem, which is like what John Stuart Bell set up here, which is, sort of what kinds of things, what kinds of physical processes count as measurements and which ones do we say are not measurements. But anyway, we will continue discussing that in the next video when I discuss sort of in more detail the Schrodinger's cat thought experiment and sort of the things that Schrodinger was actually trying to say with that in the next video. But anyway, I don't want to ramble on too long. I hope you found this video interesting, and I will see you in the next one.